though, in that black little strip at the top there. Starling forces. That sounds a little bit familiar, right? What do we already know that has the word starling in it? Yeah, we Frank Starling, right? I say I'm like 1 hour ago. It's Tuesday. It's not even Monday, right? Oh man, it's Tuesday. Let's see. So there was that Frank Starling. Wasn't forces though? Mechanism, right? Mechanism. All right. So we know all about Frank Starling mechanism, right? And that was something about the heart. So specifically, just to review, is don't get confused. The key is don't get confused. So Frank Starling mechanism was for the heart, right? And it was describing something very specific that was intrinsic to cardiac muscle fibers. What was it, basically? Length tension relationship. So when you increase the length, what does the cardiac muscle automatically, like, it's able to do?
Kick it.
Right, it's going to increase stroke volume by being able to contract harder, right? Good? All right, so we have that for Frank Starling mechanism, and that was important because stroke volume, right, that we were, let's say, increasing, was going to then, kind of already said this before the break, but if you increase stroke volume, then you end up increasing cardiac output, right? And of course, if you decrease, then it decreases, right? You work it both ways. Okay, so that's all hard stuff. Frank Starling mechanism, we reviewed it. It's separate from now this new concept, right? This new concept, which we're going to give this the name Starling forces. Starling forces. So the doctor, scientist, Dr. Starling was very busy, right, in his research, and he not only worked with Dr. Frank to develop, not develop, I don't say develop, describe, it's a better word, describe Frank Starling mechanism, and they worked on that together. He kind of had his little side project. It wasn't a side project, it was a big project. But separate from his partner, right, talking about the heart. Did some work here out of the capillaries, right? And figured out how to, in a mathematical way, figure out, I guess you could say how much influence some outward forces, outward meaning outside of the capillaries, right? How much influence outward forces we're going to have, and how much influence inward forces we're going to have into the capillaries, right? And when you put them all together, outward forces and inward forces, what was the end result going to be? Like overall, was the net result going to be, well, most of the stuff's flowing out, or overall, is it going to be most of the stuff's flowing in, right? Fluid, stuff being fluid. All right. So, we're going to look at 4 different influences. 4 different influences or factors, however you want to think about it, that lead into what is the net movement going to be, in or out. So, our first factor is going to be, we'll call it capillary hydrostatic pressure. So we're inside the capillary. We've got pressure, right? The fluid is pushing on the capillary wall, right? We know that as pressure. And hydrostatic, so hydro referring to water or fluid, right? And so we're talking about the fluid inside the capillary having that tendency to push on the wall, right? And that is an outward pressure, an outward direction of pushing. Good? So I think that's pretty logical, right, to understand. Just give it a name, right? Capillary hydrostatic pressure. It's just a big fancy long name for something that we kind of get, right? And let's also give it some sort of mathematical symbol, right? So that when we put this into a mathematical equation, we have, just a letter, right? Something like that. So our little symbol is going to be a capital P with a little subscript of a capital C. For capillary pressure is the P, right? Hydrostatic is in there, right? We know that. Good. So far, so good. Let's look at its opposite, which would be interstitial fluid hydrostatic pressure. So the fluid that is hanging out outside of the capillary in the interstitium, we know there's fluid there, right? We know that from day one, that there's fluid there. So that fluid is also pushing, exerting pressure, but it's exerting pressure onto that capillary wall from the outside, right? Because it's outside of the capillary. So you could also think of that as pushing inward, right? Pushing on the capillary from the outside, you could think of as pushing inward. Pushing inward into the capillary. All right, so here's our name, and let's give it a little mathematical symbol, capital P for pressure, and then we'll have capital I, capital F as a subscript for interstitial fluid. Great. Okay, so far it's not too bad, right? Just have these two opposite pressures, and it kind of makes sense because it's just like the fluid pushing in one direction or the other direction, right? From the inside of the wall or onto the outside of the wall. Not bad. All right, now we have two other forces that we're going to take into consideration that do influence, are we going to overall move in or overall move out? We have to talk about osmosis. We have to remember about osmosis. Remember we talked about osmosis? It was way at the end. It was like second week or something, right? Osmosis. So let's remember, what was osmosis again? It was about water, but maybe a little more specific. What about like water? Yeah. Yeah, diffusion of water from high to low concentration. So it was concentration of water. And depending on the concentration of water on either side of a membrane, and here our membrane is going to be that capillary wall, right? We might move from the higher concentration, right, to the lower concentration. All right, so it's all about concentration of water, not concentration of what's dissolved in the water, right? Different. Concentration of the water molecules themselves. All right, so depending on what is that concentration of the water, those water molecules will exert a force. It's separate from pressure. These are two completely separate things. This is dependent on the concentration. This is dependent on physically pushing, right? Pushing against the wall. So, in plasma, I know we haven't talked about blood yet, and we won't get to talking about the components of blood till next week, but we remember from anatomy, right? We should remember from anatomy some things that are floating around in the fluid, right, the water of plasma. So what were some things that you might remember from anatomy floating around in the blood? Just anything. Anything that you might remember from anatomy. I know it's a little bit not fair because we haven't officially talked about blood until next week, but let's see what we remember. Anything? Huh?
White blood cells?
Yeah, white blood cells, good.
Yeah, like ions and waste and like gases.
Oh, there's like ions and gases. That's good. That's good. We have that stuff.
We're talking about blood?
Yeah, blood.
Is it platelets?
Good. Platelets. Good. Yeah. I don't know. Any other things that anybody remembers from anatomy?
Nutrients.
Nutrients are good. Good. Dissolved, right? Floating around. Wow. Maybe we haven't said red blood cells. We should say that to be complete, right? Because we said platelets, we said white blood cells. We'll say red blood cells. Okay, great. So that's got all the cells. Okay, so we got all the cells. We have the ions, nutrients, gases. Dissolved. Super awesome. That's the stuff that's going to diffuse, right? Oh man, there's one other thing, like one category. Now that's going to be like gases. That's going to be like, that goes to nutrients, right? Nutrients, waste products, oxygen is one of the gases, carbon dioxide is the gas. But there's one other item. It was the littlest thing from anatomy. I I haven't mentioned it, and I said, well, we're just mentioning it for now. We're going to talk about it a lot in physiology, and here we are. The day has come. So, it's a category of thing. I'll give you a clue. Oh man, it's right there. The proteins. Proteins. So we had like a whole category of proteins that float around in the plasma. And I don't know, maybe if we just a little bit remembered, right? We'll talk about all the details next week. I know this is a little bit unfair. We'll talk about all the details next week. But maybe just a little bit from anatomy. There were like, there were antibodies. Those were proteins, right? And they float around. And, oh my goodness! Woo! Woo! She got it, right? Albumin, right? That was one of the examples of a protein that just sort of floats about in the bloodstream. So we have like a whole actually set or collection of such proteins that float around in the blood. And really, like their big job, maybe some other jobs, but their big job is to float around. Awesome. That's a pretty good job, right? Float around. It's like being on that lazy river, right? Good job. Woo! Nice. Float around. Yeah, if you're floating around in the water, you probably change the osmolarity, right? Right? Huh. Yes. Wow. So that's going to change this bit about the osmotic force, right? Does that make sense? By just putting in some proteins that just like take up space, really, right? We're going to change this whole bit about osmosis. So we change the concentration of the water, right? If you add more proteins, what do you do to the concentration of the water? Let's say we have only water. If we have a glass full of only water, and we dump in some little proteins in there, little albumins. What do we do to the concentration of water? Huh? Make it less, right? We decrease concentration of water, right? Concentration of water. Oh, and what did we say about water moving from one side to the other side? It wanted to move from high concentration of water to the lower concentration of the water. So, if we're going to have water on both sides, which we do, right? And if we're going to have proteins on both sides, which we will, right? We'll have proteins on both sides. Do you see how changing the concentration of the proteins, right, on either side or both sides, change both sides, could influence the movement of the water, right? So that's what these two forces are all about, these osmotic forces. Yeah, they're about movement of water, right? I mean, this is about movement of water too. But the movement of water when we're looking at osmosis is dependent upon the concentration of these proteins that are like taking up space, hanging out, right, on either side of this capillary wall. Make sense? All right. So let's give some names. Osmotic force from inside that capillary. Unfortunately, they picked pi as the symbol for both of these osmotic forces instead of like O or right, something that would make better sense, be more logical, right, like P. So we're stuck with that, right? Stuck with that. And we'll have a little subscript C for capillary. C for capillary. All right, so we have that one. And then we have this one. Ignore the arrows for just a moment. We have this name, osmotic force. That force is kind of coming from the proteins on the outside, right? Again, pi and IF for interstitial fluid. So far, so good. And now let's look at the arrows, like the direction of the movement of the water, right? Which is dependent on the concentration of the proteins, right? Okay, don't get confused. Don't think the proteins are going to move. It's the water that's going to move, right? All right. So you see how this arrow is moving in, yet this is the osmotic force that seems to be generated from the protein concentration in the capillaries, right? So what would be the situation? Let's think through it. What would be the situation if water is moving in? Yeah, so where is the high protein concentration? In. Aha. So if we have a higher concentration of protein on the inside the capillary, that means we have a lower concentration of water inside the capillary. So that water is going to try to move into the capillary to try and equalize both sides, right? Good. All right, and now let's look at the arrow over here for interstitial fluid. That's going to be the opposite, right? So we should more easily be able to figure that one out. So what is our protein concentration on the outside? We're gonna be moving water out. Yes, we've got a high concentration of protein on the outside, so the water is going to try and sort of dilute. Maybe you can think of it as the water is going to try and dilute all those proteins, right? So the water is going to move out of the capillary in an attempt to dilute the proteins. Make sense? You think of it that way. Good. So we have these opposite movements of water based on the concentrations of the proteins, right? And the water will move to the compartment that has the higher concentration of the proteins. Good? To try and even it out. All right, even out the water. So far, so good. Turns out our friend, Dr. Starling, not only defined all of these things, but defined this relationship, a mathematical equation to figure out, well, okay, we have these four things happening in all the capillaries at all times under all sorts of different conditions, right? Because we're constantly changing, right? At any particular moment, if we wanted to know, right? Well, at this particular moment, is overall most of the fluid leaving the capillary at this location at this moment, or overall is most of the water entering into the capillary at this location in this particular moment, right? So the way to figure that out was to simply add it all up. And arbitrarily, our friend, Dr. Starling, decided to give the outward pressures positive. We'll just call that positive, right? And the inward pressures, we'll just say that those are negative, right? So that we have opposites, right? Opposite directions, and we have opposite mathematical values. So all you do is add it up, right? All four. Positives, and negatives, right? Whatever they are. And you can figure out, is it going to be overall an outward movement and overall an inward movement? So here on the bottom, they're giving us a situation with real numbers. Like let's say you go ahead and you measure such things, right? So let's add a little bit of detail. Let's say that this end of the capillary is the arterial end with the arteriole entering into the capillary bed. And capillary bed, and then here, venous end, so we're exiting the capillary bed. So now we're looking at a diagram, simple diagram of, okay, now let's look at a real capillary bed, right? All right, we have to acknowledge, entering into the capillary bed, numbers are going to be different from leaving the capillary bed. So let's see. Pressure, right, of the fluid inside the capillary, pushing out on the walls, right? Let's measure it. They're giving us a number of 35 millimeters of mercury. Fine. Good enough. So we've got that. And we were going to add that with, let's go in order. So we have that, and let's add that with interstitial fluid, right? Osmotic pressure. What have they given us? 3. So this is the movement of water because of whatever concentration protein we've got hanging out here. That's so small, right? It's pretty low. All right, just plug it into the equation, right? There are those two numbers. And let's see, pressure of interstitial fluid, right? Hydrostatic pressure of interstitial fluid. So looks like they've given us, they give us 0. All right, so it turns out in this example, when we're entering into the capillary bed, looks like there's not much water hanging out in the interstitium, right? If there's no pressure pushing in on the walls, we can assume there's probably not much, right? Not much water there. Make sense? Like doing any pushing. Give us 0, just plug it in. 0. And then what's our last thing? This is osmotic pressure due to the protein concentration inside the capillary. Let's see, what did they give us? Oh, it's kind of a high number, right? Huh. Wow. Maybe there's a lot of protein inside. Look at that arrow. Looks like there's a lot of water trying to like go in, right? Huh. Wow. Plug it in. Plug it in. So our result, 10, and it's a positive 10. Positive 10 millimeters of mercury. So remember, arbitrarily, we said anything positive was going to be movement out, right? Movement out. So we can say, right, because of this mathematical equation, that our net movement is going to be outward. Net movement of water is going to be outward at this end, right? This end of the capillary bed. Kind of entering into the capillary bed. Okay, hang on to that. Let's look leaving the capillary bed. So we know a little bit from anatomy. We'll talk about it more. But in the capillary bed, we've got our exchange. Gases, nutrients, waste products, all stuff, right? We'll talk about that in a little bit. All right, so stuff happens, stuff happens, stuff happens in the capillary bed. Let's leave. Right? Let's leave after we did all that stuff. And just do the math again. Let's see what that hydrostatic pressure inside that capillary is leaving a capillary bed. You see how that dropped significantly, right? Now we're only at 15 millimeters of mercury. All right, much lower pressure. Plug it in. No big deal, right? Plug it in. Let's see, and we were going to add that osmotic force due to the protein in the interstitium. Oh. Wow, it looks like we're pulling some water out, right? Or some water's wanting to go out. Maybe there's more protein out there, over here. All right, it's fine. Plug it in. All right. Let's see. Oh man, this looks the same, right? That hydrostatic pressure from fluid in the interstitium. All right, if that's what it is, let's plug it in. It's okay. And osmotic pressure due to proteins inside that capillary, right? So a pretty heavy arrow. Oh, it's the same. Plug it in. Good. So we plug it in, we do the math. Negative. Oh, negative 10 also. Like it's kind of balanced, right? Kind of balanced, but it's definitely negative. So if overall the math comes out to be some negative number, we can say that, remember our arbitrary assignment of negative numbers, we're going to be moving inward. So overall, fluid is going to want to move in on the venous end of the capillary. Does this make sense based on like what we know so far about capillary beds, right? We want to enter into the capillary bed, allow stuff to diffuse out, stuff that is dissolved in that fluid, and then stuff, deliver, exchange, and then take that fluid back in so that we can go back to the heart. Like that makes sense, right? Okay, so this is a sort of a way to look at the details of how does that really happen, right? And the forces that make that right, that push the fluid and pull the fluid, basically. All right. So let's also notice, before we leave this slide and add even more, let's notice that, okay, they gave us some numbers, and these are realistic numbers. It seems to be balanced, right? 10 and minus 10, it's just positive and negative, but they're both 10, right? So in theory, everything should be equal. In theory, we should push an equal amount of fluid out as we take in, or you could say we should take in exactly as much as we pushed out, right? In reality, that doesn't happen. That doesn't happen. We should also remember from anatomy that because not all of the fluid just automatically returns and it's not exactly balanced, we remember that we had an entire system that was our backup plan. What was that system? So go back to anatomy. Yeah, lymphatics, right? We had a lymphatic system that was in charge of gathering all of that fluid that got left behind, right? Like, let's pretend that we left behind, I don't know, let's pretend we left behind in this location a quarter of a liter, right? Just in this little location, kind of a lot, but a quarter of a liter. Then, oh, you better get rid of that. Otherwise, we're going to have a big swollen leg, right? So that was lymphatic system job. Okay, we're going to get that. Let's see. Oh, there we go. So before we just review that lymphatic system, here we're just looking at varying capillary hydrostatic pressures from location to location, and being able, so we have hydrostatic pressure in the artery, whoa, it really drops in the arterioles, and then it drops some more as we cross that capillary bed. We already know that. And we already know, but just to like really hammer it into our heads, that we can change those pressures by vasoconstricting and vasodilating. Good, which we already talked about. Good, so this is just kind of putting it all into one graph. Oh wait, hang on. Okay. So, before we take a super quick look at lymphatic system, let's take this look at the overall distribution of blood in just a couple of examples of capillary beds, right? This is all normal person at rest. So, normal person at rest, there's in the heart, right capillaries supplying the heart. Let's see, I guess that's inside the heart. And then inside the arteries, and here are like capillary beds, right? Different locations, right? Examples of different organs. And then everything gets collected and gets dumped into venules and veins, right? We should remember that from anatomy. Look at the numbers. You don't have to memorize the actual numbers, but just get an idea and look at this huge percentage that's actually on the venous side. Venous side. So I don't know. I think that should be a surprise. I feel like it's always a surprise to people, because people are usually think of like, ooh, the heart pumping out stuff, right? And then like when we do our exercises, you feel the heart pumping out stuff, and we keep thinking of the heart supplying blood, right, to things, organs, skeletal muscles, whatever, right, brain, whatever. And we always sort of forget the veins. They're kind of boring, not really so active. They just collect blood, bring it to the heart. Everyone always blows them off, right? Veins. Oh man. Well, it turns out for physiology, like, yeah, for anatomy, it was always like, you learn the arteries really well, and it was like, oh yeah, the veins, they just all have the same names. Remember? Right? They just had the same names as like the arteries. Okay. But physiology, veins actually turn out to be quite important to the cardiovascular system and how this is all actually going to work and how this heart is going to function. Super dependent upon veins. and this huge amount of blood that actually even at rest is hanging out, right? In a healthy person, most of our blood's hanging out there, right? On the venous side of things. My goodness. Let's look at some stuff over here, some details. We've got a venous pressure, right, on this whole entire venous side. As we're collecting all that blood, a pressure that we can measure, 10. Oh, that should sound familiar, right? From the previous slide. We kept picking 10, right? All right. So anyway, we can measure on the venous side, we collect stuff, 10 millimeters of mercury. If we were to, and you certainly can, measure the pressure inside that right atrium, of course, right atrium is accepting all that blood, right? 0. That's a surprise. We didn't expect 0. 0 doesn't really sound good, right, as far as blood pressure is concerned. But in the right atrium, that's fine, right? That's fine. The differential between the veins, right, at 10 millimeters of mercury and in the right atrium 0, that's a differential of 10, right? It's good enough. It's good enough to generate flow, isn't it? Remember when we first talked about flow last week? Blood flow through a tube, capillary, whatever, any tube, doesn't matter. Artery, vein, right? All you needed was a differential between pressure here and pressure here. As long as there was a differential, you could move the fluid, move the blood, right? So here we've got a differential of only 10. It's good enough, right? Differential of 10, we can still move stuff, right? We still get the fluid to flow. All right. So we use that on the venous side, that small differential to keep the blood flowing to the heart. But do you see, because it's a small differential, we're not like, it's not like a tidal wave, right, coming at that heart. It's a nice, right? It's a little, the nice waves, right? On a nice day with the little waves and whatever the moon's doing, I don't even know how that works, right? But you know, some days you have the nice waves, like those waves, right? Not the big tidal. That's good, right? We don't have tidal waves coming at our heart, right? Oh no, nice. So, what would happen? What would happen if, for some reason, we did have a tidal wave? For some reason, suddenly, we increase the amount of blood flowing into that right atrium. Like I said, tidal wave, all of a sudden, whatever reason, it doesn't matter. All this blood coming back into the heart. It's going to enter in. I mean, right atrium's at 0. Whatever comes at it is whatever comes at it. So it's going to take it 0. So that'll enter in. Maybe think back to the heart again. What can we call that? Like the blood coming back to the heart and like filling the heart. We're on the venous side, but we're still filling the venous side at the same time that we're filling the arterial side, the left side, right? And in our heart discussion, we did a little bit focus more on like left, right? But there was a slide in there that looked at the right side. Oh my goodness, remember that? Yeah, remember all that stuff? Oh, Wiggers, and then there was that extra slide after the official Wiggers diagram that I said, oh, like the Wiggers is focusing on left side, but the same stuff happens on the right. It's just all the pressures are way lower. Remember? Let's look back. Let's look back. Hang on. Let's see. Oh my God, where was it? Oh, where's that? Oh, Wiggers.
It's up above 25.
Oh, okay, here. Cool. Oh yeah. Huh? Remember that? And the pressures were so much lower, right? Alright. Just a reminder. So, let's try and put everything all together, right? Wigger is on the left side, and then this thing on the right side, and now this new stuff about veins, and the right atrium being at 0 pressure, right? 0 milliliters of mercury pressure, right atrium. And tie that together with filling the heart. Filling the heart. What happened when we... Okay, wait. Oh, okay, yeah, so let's start with what's the name? Okay, let's start with the beginning. So what is the name of, like, okay, we fill the heart and we're full. Okay, so end-diastolic, ventricular volume, and we did have another word for it. Preload, good, preload. All right, and we know that if we filled it more, we already said this, we will automatically
Eject more.
eject more by increasing stroke volume, right? And then we increase, therefore, good cardiac output. I know we said this already. Okay, good. Good. Got to keep this in the head. So far, so good. So now we're thinking. Because we're talking about veins and returning blood to that right atrium. If for some reason that we haven't even said yet, but if for some reason we increase that volume of blood, right? It's returning, entering into that right atrium. So we're increasing from the veins, right? From the venous side, we're really looking at that. For some reason, we send the tidal wave, right, up onto the beach instead of the nice wave, big storm, right? Send the tidal wave up. Oh, now we're increasing, right? Would you say? We're taking in more blood, so we're going to be increasing preload. Oh yeah, and then the same old stuff's going to happen, the same old stuff that we know. Increased stroke volume, increased cardiac output. Make sense? Just kicks in automatically, right? Like a Starling mechanism. Wow, we keep saying the same things over and over again, but that's good, right? So I want you guys to tie this together. Good? All right. Huh. When might that happen? Like suddenly you just send a tidal wave back to the heart. I don't know. I don't know. Huh? Yeah, exercise, right? I mean, just it doesn't have to be anything like a big deal, right? It's an exercise, right? Even just our little thingies that we did, right? Our little jumping jacks. That was enough, wasn't it? It was enough. Kind of good. Kind of good. Isn't it good that even if we do just a minute of jumping jacks, right, we could increase the amount of blood, right? We're going to see how we're going to increase the pressure there to push it, right? We're going to increase the pressure there to push more blood into that right atrium, which stays at 0, right? Increase the preload, and Frank's Starling mechanism kicks in, and we increase stroke volume, we increase cardiac output. Oh, we're doing a minute of exercise. Good thing we're increasing cardiac output, right? You see how it goes around and around in a circle? Okay, good. Good. So we're starting to get somewhere in this discussion that we can apply to real life. All right, we're starting to get there. Okay, and it's all like automatic. We have not even bothered yet to, with just our simple exercise, right? We have not even bothered to like, oh, let's do something sympathetic, blah, 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 right? We just start doing a few jumping jacks. Good? Make sense? So far, so good. All right. Let's just make a little note before we leave this slide. And there is just a tiny little bit of smooth muscle in the walls of the veins. So we could get, speaking of sympathetic, right, we could get a little touch of sympathetic stimulation right? Onto those, we're going to have alpha receptors there. Two, what would that do? Alpha receptors.
Contract.
Huh? Yes. So on the veins, right? Same thing. We'll get a little bit. It's not going to be anywhere near as dramatic as arterioles, but we'll get a little touch. So that will help also. Sympathetic stimulation will help push, right? Just a little bit of that blood back to the heart. That's a good way to increase preload, right? If you're nervous, now maybe not exercising, but just, right? Remember before the exam sitting there nervous, right? Get a little blood flowing. Make sense? All right. So far, we're getting there. Let's see. We remember from anatomy another way of helping blood to return to the heart was using the muscles and allowing them to push. So we remember that from anatomy. And here we see a summary of all of the ways that we can get blood to return to the heart. So, and ultimately, right, if we increase these ways, we can increase that stroke volume, et cetera, which we've been reviewing. So, we know about sympathetic stuff. We know about skeletal muscle pump. We just saw that picture. That was a little review. We know about increasing that blood volume, right? Pushing the blood to that right atrium. And here's one other way that we have not yet talked about, but let's talk about it now. It's increasing inspiration. So what's inspiration when you breathe in, right? And we know, I know we haven't done respiratory system yet. We're going to do that. But from anatomy, we should remember the diaphragm, right? Was our big deal, right? Big deal breathing muscle. And when the diaphragm contracts, it flattens, right, to increase the volume in the cage, right? But what does that do to the volume in the abdomen when you go from here, right, the dome, to the flat diaphragm to breathe in? So what happens to the volume in the abdomen? Decreases. So this is going to increase, this is going to decrease. We've got a differential, don't we? Right, that creates a differential, right, in pressures. So again, differential in pressures is going to encourage blood to flow. It's kind of coming from the outside. It's a little bit indirect, right? But it counts. It counts. So breathing in, the big breath in with that diaphragm creates a differential. If this is higher and this is lower, the blood's going to flow toward the heart. That's what you want, right? That's what you want. So if you increase the respiratory rate, jumping jacks, that example again, right? Increase the respiratory rate. Are we doing this more? Right? So every time we breathe in, we encourage blood to return. Every time we breathe in, encourage blood to return. Make sense? So exercise just by increasing the respiratory rate. You also have like this extra way of getting blood to return. You want that, right? This is all part of the same thing. You want that, increase the preload to increase that stroke volume. Good? And cardiac output from there. Good? Like we could put another thing here. Cardiac output. Awesome? Okay, so far so good. Woo-hoo. Here's our reminder slide of lymphatic system from anatomy. Just be sure you remember lymphatic system, which is in charge of taking all that stuff that, whoops, right, stayed in the tissues or in the interstitial fluid. Here's our close-up review from anatomy again of how a lymphatic capillary works. So be sure to remember that from anatomy. And that brings us to the end of today's official lecture stuff. We're going to do our blood pressure lab. This is where we're going to pick up on Thursday, mean systemic arterial pressure. I think this is slide 67, 66 or 67, somewhere in there. Good. So, the blood pressure lab, you can stay, like in our groups is fine. Each group pick up at least one stethoscope and at least one blood pressure cuff And if you want to, there are also alcohol wipes there if you want to wipe off the ear pieces for the stethoscope. So everybody grab one of those.
So mad because I was sitting next to it this morning.
Before anything.